nervous tissue chapter. I'm trying to remember exactly where I stopped. I kind of remember on last Tuesday saying, it was like 10 minutes left, and I didn't want to start the next thing. Right, okay.
Yep.
So did I talk about the action potential and I was getting ready to go into graded potentials, or was it? I haven't talked about graded potentials. So let me just, oh, shoot. Oh, I know what I want to do. Something else I want to do, but so I used videos. We went through this stuff and talked about how, but here's the book's representation of the action potential curve. And I want to go through this and make sure that I've covered everything sort of. This will be at least review, if not making sure I covered it. So we start off and the cell's at rest. Okay, this is resting potential, -7. And then some sort of stimulus is applied. What type of stimulus can that be? Should we talk about that? Really? I don't remember talking about that.
Very chemical or electrical?
So, wait, what was that second word?
Electrical.
Well, and you said chemical, the first thing, right? Yeah. So really that's one thing, electrochemical, which would be another axon making a synapse on this neuron and releasing neurotransmitters. But when I was talking about the types of channels, there was the ligand-gated channel, the mechanical-gated channel, the voltage-gated channel.
Yeah.
So those first two would basically be what the stimulus would be. So what you're saying actually is one thing, which would be a ligand-gated channel. The ligand, the neurotransmitter that's released, is because of the electrical activity in the previous cell. But you could also have a physical stimulus like touch that activates a mechanically gated channel. That thing looks kind of like a trash can with the lid popped up. There are other things that could do that, but for what we've talked about so far, those are the two examples of the stimulus that can be applied. And that causes the membrane potential to change and become less negative. And it reaches this point here, which is called threshold. What happens at threshold? What is threshold? Talked about this? Words come up before? Does nobody have threshold in their notes? Did I just dream everything?
I remember it on a homework or a quiz. I don't remember.
One gate closes and the other one opens.
That's what it's about.
File for it to switch to the light.
Well, you're actually putting two things together.
Okay.
The first thing you said, one gate opens, the other closes, or whatever. You're talking about the voltage-gated sodium channel. Okay?
Yeah.
The way you said it technically isn't correct, but that's because it's a very confusing channel. But what threshold is that's the voltage that causes the voltage-gated sodium channel to be activated. So the activation gate opens. that means that sodium rushes in and the voltage rises. Okay. What's the term we use that actually means when the voltage rises or the charge of the membrane gets less negative? This upward part of the curve.
Depolarization.
Right, depolarization, which is due to sodium entering. From rest to threshold, the sodium entering is probably coming through a ligand-gated channel or a mechanically gated channel, for the examples we talked about before. Depends on the exact stimulus. But something lets sodium in. Once it hits threshold, that's what opens the voltage-gated sodium channels, and we have sodium rushing in very quickly. And it hits its peak at positive 30, which is the values that we've been using here. And then the second thing we were saying, Monica, about the delay, that's the other type of voltage-gated channel, which is the potassium voltage-gated channel. Yeah. It's gated at negative 50 millivolts, okay? But it doesn't open until we hit positive 30. And the reason it doesn't open until that voltage is reached isn't because of voltage, it's because of time. It's really about half a millisecond after it hits its gating voltage. And so if we just go over about half a millisecond on the time scale, which is not easy to tell because there's not tick marks on the time scale, but trust me, that's a half a millisecond, that's when it's gonna open. Okay, so it's that other type of channel is delayed. And so it opens here, which corresponds with when we hit the peak of the action potential. What else happens at the peak of the action potential? Back to the sodium channel.
The sodium channel closes the potassium open.
Right. What part of the sodium channel closes?
Like an activation channel.
Right, so we open one gate here, the other gate closes there. So this is the activation gate, this is the inactivation gate. But then you went on to say that the potassium channel opens, and that's true, that's happening there. So potassium's leaving the cell, which causes the voltage to drop. Okay, what do we call voltage drop or fall? Repolarization. Right. Now, because that voltage-gated potassium channel's got a little bit of delay in it, when we go back past negative 50, which is going to tell that channel to close, it doesn't actually finally close until about half a millisecond later. And in that half millisecond delay, the potassium rushing out actually causes the membrane voltage to drop below resting potential, which is the hyperpolarization. Oh, I meant to ask that question too. I asked you depolarization, repolarization. Hyperpolarization is this one. So at this point, at the very bottom of hyperpolarization, the voltage-gated potassium channels are closed, and we return back to resting potential thanks to the sodium-potassium pump, that thing that uses ATP to pump sodium out of the cell and pump potassium back into the cell. It returns everything back to where it's supposed to be. Now, that's actually always going on. It's just that during the couple of milliseconds that all of this takes place, the channels that have opened, the voltage-gated sodium channel for depolarization or the voltage-gated potassium channel for repolarization, the ions are moving so strongly through those channels that the sodium-potassium pump doesn't have an effect. But once everything's closed off, then we get back to rest. Everything's happy. So, other than the vacant stares when I ask some of those questions, that's all stuff we covered already, right? Okay. So, over the weekend, I did not get to do the recording I wanted to, but I did get close to doing that. I've set up the presentations for, well, I did the first recording section. Isn't that useful? It's just the divisions of the nervous system stuff. But I've set up all of the presentations for the total of 7 recordings I'm going to make for this chapter. And in doing that, I came across some stuff that I want to show you that will hopefully allow for a better understanding of things. Okay. The first recording that I did is really just the stuff down in this bottom box, which is about central versus peripheral and sensory versus motor and what's the other one? Somatic versus autonomic. I will go on to make a recording about the tissue. I think there's actually 2, one about neurons and one about glia. And then I'll go on to do recordings of this stuff about excitable membranes. I drew on the board last time my little cartoon representation of the voltage-gated sodium channel with the 2 gates. I had one on the inside, one on the outside. It was completely a cartoon representation. It wasn't at all realistic. So what I wanted to do was, I was putting this together, was to come up with a good image to represent that channel. So I started searching for images of that channel, and I found several that would not be appropriate for this kind of presentation, but about its actual protein structure. And as I was going through looking at those, I found this picture here. Now, this is obviously in the same style as the pictures that we have in our book, made by the same art department. It looks kind of like the voltage-gated potassium channel picture that it's in the book that I used and showed you. I have always been a little bit baffled by the picture that the art department made for that, in that it had the this part sort of in the middle and this ball and chain kind of stopper part. Most representations of voltage-gated potassium channel that I've seen are going to just have that sort of ball and chain stopper part. That's all that's really necessary. There doesn't need to be another part. And I discovered why, well, I think I figured out why they made that weird picture, because they were actually drawing the voltage-gated sodium channel, but then they didn't quite do it correct. I didn't know what they were drawing. I didn't understand it exactly. But it turns out, and now that I've looked at actual pictures of the representation of this channel's protein shape, I understand what they did. This is a picture of the voltage-gated sodium channel. The 2 little things sticking off to either side are the inactivation gate, and the ball and chain is the activation gate. And actually, as I start to explain this to you, I realized that there is a mistake. The inactivation gate should not be closed at rest. It should be like this, but with the ball and chain stuck in there. And I'll have to fix that at some point. But what they are showing is at rest. Oh, I see. Never mind. I got them backwards. So this is the activation gate. This is the inactivation gate. So yes, the inactivation gate is open at rest, but the activation gate's closed. And so once we hit threshold, the activation gate opens, and now things can move through the channel. Okay. I added in this, which is from the pictures in our book, to show the concentration gradient. They didn't have that in this picture from the source I got it. And then it's inactivated. It actually doesn't say when, but when it hits that peak of positive 30. So this is it in its resting position. The activation gate's closed, inactivation gate's open. This is it after threshold, when sodium's rushing in for depolarization. Both gates are open. And then this is the inactivation gate closing off the channel when it hits peak. Okay. It'd be kind of nice for this picture if they went on to have a picture with everything closed, sort of to close out, to finish off its cycle. What happens at the end of repolarization, so that it resets. But for whatever reason, I don't have this. This is a pretty good representation of how there are two gates. Now, where I found this was actually in another book by the same group, which is that OpenStax thing. Let's see here. Oh well. I'm just opening up another page with the publisher's website. They have a couple of biology books. This one called Concepts in Biology is the type of book that would be used by our non-majors biology course, what we call Principles of Biology. And then, where's the other one? Did I miss it? Oh, there. The one that's just called Biology would be used by a majors level course, which is, I think we call it like General Biology or something like that. It's Bio 201. And in here, they have a unit on anatomy and physiology, and each section within the chapter sort of covers an organ system, or each, whatever. It's dealing with all of anatomy and physiology very quickly. But then they have the section here that's how neurons communicate. And you can see right here that there's that picture that I just used without the arrow showing the concentration gradient. I'm pointing this out because if you'd like to find another source that sort of discusses the same things that we're covering in this section, you can go here. Actually, I think the first paragraph here is the exact same first paragraph from the chapter in our book. So I think what they did is they took the chapter that I put together and they had another author sort of adapt that to this book, which I'm not at all upset about. I would have liked to have been told that they were doing it that way, but more because they made some new pictures for this, which I think would be better for the book, like this voltage-gated sodium channel one. But they go through and explain things a little bit. This picture shows you the state of the resting, it shows you this, what would that be? Rest, depolarization, and repolarization of the action potential. They use different numbers. They use -80 and +40 instead of -70 and +30, which isn't necessarily wrong. It's just less common. This is the curve that we just looked at, just labeled in a different way, like using the words depolarization and repolarization. Actually, it doesn't have depolarization in it. Interesting. This picture is new, which I'm going to use because it's good for what it shows. This kind of addresses the same thing, but I don't think it's that great of a picture. I like this picture. It's just showing the vesicles inside of an axon terminal. I was pausing for a second because I couldn't remember if it was vesicles inside a terminal or neurotransmitters inside a vesicle, but showing you that. This is essentially the same kind of picture that I have of the synapse. They just included two insets, one of a ligand-gated channel, which is not a very good representation of a ligand-gated channel. And then another thing here, which is actually kind of cool, it has a few different possibilities of what happens to neurotransmitters afterwards. I discuss that stuff in the book. I just don't have a picture to go with it. And then it talks about synapses. I have a table in the book that that sort of lists the different types of neurotransmitters, which is not very good. And this version of it isn't a lot of an improvement, and mostly because they leave out what I think is an important aspect of it. So I made a new version of the table, which is in the presentation, which I'll show you when we get to that. And then this is the stuff about graded potentials, which I'm going to talk about in a little bit. And this is, in fact, a picture, again, out of the chapter that we're dealing with. And then this stuff down here, I don't touch this. I think this is going too far into nervous function for a course like this. And I'm surprised that a course like that, which is dealing with all of A&P topics within one unit, bothers to go into this. But if you're interested, this is sort of talking about some aspects that interact with, that apply to how neurons are involved in learning. So just want to point that out. Again, if you're interested in looking at another source that kind of describes a lot of the same things, similar to the book, but maybe a little bit differently. If you're having trouble understanding the chapter as I've written it, you might go here and just get another perspective. Just within our book, if you click on the icon here for OpenStax, CNX at the top corner, it'll take you to a list of all their textbooks, and the one that's just biology, not concepts of biology, but biology, has this chapter in it. So, I want to cover a couple of other things about the action potential, and then I'm going to get to what graded potentials are. This is a picture I just pointed out that was in that other chapter. Oh, shoot. So in the voltmeter picture that they have here, they're using -80 and +40. Just pretend that says -70 and +30. Those are the numbers that we're working with in this course. I'm just showing you at rest. It's at that negative number. At the peak of the action potential, it's at the top. And then after the action potential, it drops down. In this, they have this thing here representing the sodium-potassium pump. And this is a really, really bad rendition of it because it's not a channel, it's a pump. And in the video that I showed you last time, it sort of showed you this thing that opened and closed at both ends. That's a better representation of the idea that it's a pump. And then they have the potassium channel and the sodium channel here. These are supposed to represent the voltage-gated channels that we're talking about. Why the cartoon representation of this is different than the way that they draw channels for all the other pictures in the book, I don't know, but that's what they did. It does show you during depolarization, sodium's rushing in. During repolarization, potassium's rushing out. It doesn't address the idea of inactivation of the sodium channel or anything like that. It doesn't really address, well, it says hyperpolarization here because the pointer is a little bit below the resting value. You can see it there. But it doesn't really address the little delay there that causes it to close late. So graphically, it's a little bit strange compared to the other pictures that are drawn from this book. One, I think, kind of obvious thing is for the cell membrane and all the other pictures, that actually kind of shows you a few layers of phospholipids, kind of like three-dimensional going into the background, and here it's just one flat line there. So a different artist must have decided to do this, whatever. But it does kind of point out the major things, just understand that some of the drawing's not really there. Okay. In the book, oh, actually, I guess this does introduce that. In the book, I did this, which I've gotten a little bit of feedback that seems kind of strange, but we looked at essentially this graph a second ago, but we looked at the labeled version. what I did in the book is I wanted to introduce just the basic idea of depolarization, repolarization, hyperpolarization. So I have this figure with those labels. And then I explain what's happening in the action potential, and following the explanation, I have a new version of that graph, which is the one we were just looking at. And so there are numbers there corresponding to a list of the events and a description there. So that's why there's sort of two versions of the same picture there. One was just early on setting up what the action potential is in very broad terms, and then a second version came later on with the labels here. Okay. Now I just noticed as I was going through this that this picture came up in the path before those graphs. And I just need to fix that. But this is a picture out of the biology version of the book. And it addresses something that I actually kind of left out of the book that we have. And so I'm glad that I found this picture because it kind of addresses it. So, and that's what's called propagation of the action potential. Now, the word propagation is a noun form of the word propagate. And propagate is the verb form of the noun propaganda. Okay, what is propaganda? Not a science.
Information.
Right. Generally, when we think of propaganda, it's lies that the other people tell us. Okay. Now, really, the word propaganda is a bit subjective. People at Fox News will tell you that they're telling you the truth, but people on the left will say that Fox News is spreading propaganda, vice versa, whatever. So it depends on what side of an issue you're on, who you think is right and who you think is wrong. But propaganda has this kind of negative connotation of, how did you say it? Misinformation?
Misleading.
Yeah, misleading information. So again, it does depend on what you believe to be the truth, as if truth were a subjective term. But the important part about the term propaganda is, which isn't exactly the way that you described it, is spreading misinformation. Okay, so propagation means something similar to spreading. Okay. And so we're talking about the action potential. Propagation is sort of how it travels. It starts at the beginning, at the axon hillock, and it spreads along the length of the axon to the axon terminals. And these pictures kind of show you how that happens. So the sort of tannish color that's labeled resting in the bottom two parts represents the membrane in those regions that's at rest, nothing's happening. And then green for depolarization means sodium's rushing in, okay? And its positive charge makes the inside positive versus the outside. The arrows that they show going either direction represent the path that those sodium ions take. So when sodium comes into the cell, it'll diffuse either down or back up the axon. The ions that diffuse down the length of the axon will depolarize the next region and allow those ion channels to open up so more sodium can rush in and diffuse down further, causing the next region to depolarize too. Okay, that's propagation. Sodium enters here and diffuses along the length of the axon, and when it gets here, that'll make this more positive, and so sodium, voltage-gated sodium channels will open, sodium will rush in, and they'll spread down, keep going. But there are arrows pointing the other direction. Okay, so sodium will come in and go either way. It's completely random which way it diffuses. But if it goes back this way at the axon hillock, and goes into the soma, it won't really have an effect. It'll depolarize the soma, but there are not voltage-gated sodium channels in the rest of the cell. They're only in the axon. Okay. So sodium going this way doesn't really cause anything to happen because there's no way for a lot more sodium to get in. And then if we get to here, we see the next region depolarizing. Sodium is going to go back this direction, but what is that, kind of a turquoisey color there? That's labeled repolarization, that's when potassium's rushing out. Okay. And this area that just depolarized is now in the refractory period. Okay. So even though sodium goes down this way, potassium rushing out keeps it relatively negative, and you can't open voltage-gated sodium channels here because everything's in the refractory period. So that means that sodium diffusing in, which can go either way, only has an effect going down the length of the axon. So it'll depolarize here, and then it'll depolarize here, and then the next part will be depolarized if we had a fourth part of this, and just keep depolarizing down further and further. Okay. That's propagation. The action potential can't go back the other way because the previous region that just depolarized is repolarizing and therefore is in the refractory period. And with potassium rushing out, you'll not get to threshold and open more sodium channels. If it were to happen that an action potential starts in the middle of the axon, if it starts here, which can happen artificially if you put an electrical wire next to a nerve and send a jolt of electricity into it, you'll depolarize the axon at that point there. Sodium will rush in and diffuse both ways. Since it started here, that means that back towards the cell body end is not repolarized from a previous action potential or from previously depolarizing. So sodium rushing this way will depolarize this, and sodium rushing this way will depolarize this, and you'll get the action potential actually traveling in both directions. That's very artificial. Okay, it's not every day that somebody has an electrical wire stuck in the middle of a nerve to do that. Okay. So that doesn't happen. Under natural conditions, under normal conditions, action potentials always start at the axon hillock, which is the first place that we see the voltage-gated sodium channel. So any sodium entering in here that goes back into the soma does not have an effect because you can't have action potentials here. It has to go that way. And once it started here and moves down, it won't be able to go back because everywhere the depolarization is spreading, on one side there will be repolarization happening, and we can't open new sodium channels there because of the refractory period. Do you get that? Okay. There is a video of this, which I hope I can find. What's that? Refract. Oh, that's not what I wanted. Action potential propagation. Okay, so I'm going to go to this. This is an A&P Flicks movie, which is from the Pearson set. So I'm going to play that, and then you can see right after that, well, there's a couple here that I've watched before that are pretty short, a 2-minute and a 49-second video that are other representations of that. Okay. Oh, we need some sound.
Action potentials propagate in a continuous fashion in unmyelinated axons. Once an action potential is generated in the initial segment of the axon, it propagates the entire length of the axon. Recall that a threshold stimulus causes voltage-gated sodium channels to open. The influx of sodium ions generates an action potential. It also establishes a depolarizing current that flows to the next segment and brings it to threshold. Voltage-gated sodium channels open, regenerating the action potential in this segment of the axon. Current flows from this segment and depolarizes the next segment to threshold, thus regenerating the action potential yet again. In this way, regeneration continues in one direction all the way down to the axon terminals. The basis for unidirectional propagation is revealed when we take a closer look. By the end of the depolarization phase of the action potential, all voltage-gated sodium channels inactivate and voltage-gated potassium channels open. These two events render this segment of the axon temporarily insensitive or refractory to another depolarizing stimulus. However, voltage-gated sodium channels in the downstream segment are closed and receptive to a depolarizing stimulus. Thus, propagation occurs sequentially down the axon to the axon terminals. In myelinated axons, action potential propagation is a bit different. Here they propagate in a saltatory or leaping fashion. The myelin sheath consists of multiple layers of tightly wrapped glial cell membrane. But this sheath is not a continuous one. Exposed areas of axonal membrane, known as nodes of Ranvier, occur at discrete intervals. Voltage-gated sodium channels are abundant in the nodes, but largely absent between nodes. So, action potentials are regenerated at each node, not in areas covered by the myelin sheath. However, the myelin sheath does provide the insulation necessary for the rapid spread of depolarizing current. And the sooner the nodes reach threshold, the faster action potentials propagate along the axon. Saltatory conduction is extremely fast. Velocities often exceed 100 meters per second. In contrast, continuous conduction is fairly slow. Velocities rarely exceed 2 meters per second. Nevertheless, both continuous and saltatory conduction propagate action potentials over varying distances because action potentials regenerate along the way. Summary: propagation of an action potential. Once generated, the action potential propagates the entire length of the axon without decrement.
Okay. I want to go back and show a couple of things from this because they kind of included some interesting things in here without saying stuff about it exactly. Now, the first thing doesn't quite fit in that category, but it does echo something I was showing you before. This red channel is the voltage-gated sodium channel, and they have both gates represented. This is a little bit blurry because I caught it in a weird frame, but when they're closed, when the activation gate is closed, which is not what we see in this frame right here, the middle of the channel is kind of pinched in. Now, in the picture that I was showing you, that's essentially from our publisher, they have those two things on either side that kind of poke in, but it's in the wall of the channel. There's something that kind of closes off the channel, which is, and they represent that. And then they have the inactivation gate, which is the ball and chain here. For the voltage-gated potassium channel, the channel pore is just pinched closed. It doesn't have anything else there. It just opens or closes based on that. voltage gating. Okay. And they don't say anything here about the half a millisecond delay that I've been talking about, but it is true. Now here they're showing, and this is common, we've seen it elsewhere, the action potential is represented by a bright glowing part of the membrane. What they don't really point out here, but I kind of like the choices they made artistically, where it's brightest right here in the middle is where the action potential is quickly depolarizing and reaching its peak at positive 30. Downstream towards the end of the axon, the next region is yellow also, but not quite as brightly shining as what we see, because this is what's starting to depolarize. It hasn't really started moving toward its peak, but this is where it's going to happen. And then posterior to that, they have a black shadow showing that the previous segment that might have just depolarized is now repolarizing and in the refractory phase. Okay. They do a good job of explaining the idea behind the refractory phase. So they show that the voltage-gated sodium channels are inactivated, the little ball and chain thing stopping up the inside surface, and the voltage-gated potassium channels are open. I don't know how well you can see it, but there's a potassium ion represented here moving through that. So those two things render this area temporarily insensitive or refractory. Okay, we talked about the refractory period last time. We did talk about the refractory period last time, right? Because I remember I showed you that video with the British guy, and I showed you that what he called the refractory period was not the entire refractory period. So, okay, good. Want to be sure there. But then if we move down the membrane, so we go past what's in the action potential, glowing bright, into the downstream part that's at rest, as that yellow starts to spread in before it gets bright because the sodium's rushing in, that's where it goes. And so that makes sure that things only go one direction. Now this is another thing. Let me try to capture that better. Not going to quite do it, but. So everything they talked to up to this point is about continuous propagation, which is happening in an unmyelinated axon. And then they pull out and we see a myelinated axon. I don't think I'm going to be able to capture the frame exactly where they show propagation down the myelinated axon with the background image of continuous propagation here. This is what's called saltatory conduction or saltatory propagation. Saltatory means essentially leaping, because what happens is we can measure the action potential at this spot here, and then we can measure it at this spot here and at this spot here, each node of our VA going down. If we were to measure the membrane potential in between, we poke through the myelin to measure the inside voltage of the membrane versus outside, we would not measure that there's an action potential going on in there. Okay. We probably see some depolarization, but it would not really be an action potential, the events that we've been talking about. What happens in myelin is the sodium gets in at the node of RNVA, and it's going to diffuse just like we talked about a little bit ago, but it can't get out of the cell where there's myelin wrapped around. So the next place, so the sodium is sort of forced to go down the length of the axon to the next node. And the distance from one node to the next is just the right distance for that sodium to still be able to depolarize the threshold. If the next node was a little bit further on, if the sodium got down that far, it would only depolarize to, let's say, 60 millivolts, which is not threshold. So more sodium channels would not open up. That location is sort of the perfect distance between nodes for the next set of voltage-gated sodium channels to open. Okay. Did I talk about that at all last time? I talked about 3 organisms, one with too far a distance between nodes, one with just the right distance, and one with too short. Oliver remembers it. Anybody else remember it?
I wasn't here, so I don't know.
Okay. So it sounds like it's this perfect setup, but it just comes of years and years of adaptation. Organisms with shorter distances between nodes of Rambier, action potentials will propagate, but they'll propagate slower because it has to go from spot to spot to spot to spot more often than further distances. And so just normal variation in genes in organisms would present some organisms that have further distances between nodes of Rambier. And up to a point that it'll improve the rate that the propagation takes place. So in the video there, they just said more than 100 meters per second. Okay. So let's say another organism with closer nodes of Rambier would only propagate action potentials at 80 meters per second. Okay. It's still a fast time, but that little difference might be enough for one organism to get away from a threat and the other organism not to, and it'll die and not pass on its genes, and the one that got away has offspring that are going to now make faster axons, and that'll become common in the population, and we end up over the eons of time that nervous systems have developed to get sort of the perfect distance. Okay. The other, I wasn't going to capture, let me try it anyways. There we go. Not quite. There we go. So what you saw was a flash at each node of Rambier, which I captured one of them here. The frame I just kind of captured a second ago. You can see a little bit of glowing within where the myelin was, but not as bright there, because there is depolarization. It's just not what we would really call the action potential. The action potential is regenerated as we get to each node of Rambier. Okay. Then at the end, they had the summary thing. And what they did here is actually kind of clever, again, subtle, and didn't really make the point of it, which is, let me go back. They draw in the myelinated axon at the top, and then they have the, curves. Try that again. They have the curves of action potentials there. And notice that they're flashing in and out. They show one here, and here, and here, and here, and they line up to where the nodes around BA are. Because in between two nodes, you're not going to see these events taking place. Okay. So they just show them popping up in sequence, going down there, and corresponding to where we see the bright flash at the node. Now, sodium's coming in here, and it's diffusing to the next node. Okay. Sodium's coming in here, and it's diffusing back to the previous node also. But the previous node is going to be in that refractory period. So it won't start an action potential or regenerate an action potential back this way. So that means it can only move one direction. And sodium can't diffuse past that next or previous node of Rambier to the one before that, because that's too far for sodium to have any effect. But so they show that sort of jumping, saltatory, leaping, whatever effect as they animate that. What do we call that? Summary figure. Okay. Now, in the search I just did, there are these other two here that I'm not going to play here, but I'll put them into the presentation. I don't like to put the Pearson copyrighted things into my presentations because that's a copyright violation. And I actually don't know offhand about these other two. I'll have to look at those more closely. But I just feel really funny about showing you Pearson material when I'm telling you not to give Pearson money. So I'm not going to do that in the presentations I make. So if you're interested in watching those, I'll have links to them, or I'll have them embedded in the presentation when I get around to doing that part. Seems like there was another thing I wanted to mention about that. That's right. I want to remind you the tissue slides that we looked at in lab. I showed you this one specifically because it shows a good representation of the distance between actual nodes. I really hate this little dialog box that comes up. Didn't used to do that, but anyways. So we can see a node of Rambier right there, and we can see a node of Rambier right there. In the pictures in the book and in the animation we just watched, the myelin looks like it's a lot shorter. Okay? It's necessary for the way that we draw these kind of pictures for the scale to be off, for the diameter of the fiber. The distance from one to the next is really quite far. Think of what they did is they just made the fiber in their drawing a lot thicker so that we could see. So we could see some detail. But this is really how far apart those nodes really are. Okay, so sodium rushing in at this node is going to diffuse either direction, and it'll diffuse through to the next node up here. That membrane will reach threshold, and sodium channels will open there and will regenerate the action potential. And then that sodium will rush in and diffuse to the next node that way. It will also diffuse back to this node, but this node is in the refractory period, so you can't start or regenerate an action potential there to go back. It has to go that particular direction. So I just want to remind you of that. Now, the next part of what we want to talk about is called graded potentials. Now, I defined these terms for you earlier. Let me just remind you of this. A graded potential is a change in the membrane potential, or the charge across the membrane, that's entirely dependent on the size of a stimulus. Now, I kind of do something that probably upsets your average student sometimes, that I tell stories kind of out of order, okay? I did this to some degree with muscles. I talked about contraction, and then I went back to include excitation, okay, to give you the whole story of excitation, contraction, coupling. And then here, I'm talking about the action potential, and then I'm going back to talk about graded potentials. That stimulus that gets us from -70 to -55 is a graded potential. Okay. Now, graded potentials can be caused by stimuli directly in receptor cells, and I think I defined that, the receptor potentials. Or they can happen at synapses. And so those are the postsynaptic potentials. So in this first picture here, this is kind of a graph showing graded potentials, similar to the graph that we looked at action potentials. Now, what I have them do is draw a series of graded potentials of different height. So a small or weak stimulus will cause a little bit of depolarization, but only to, say, -64 millivolts. Okay. A stronger one can get us up to -60, but still, that's not enough to do anything. One of, this kind of bothers me, this line is supposed to be equal to that line height, but let's pretend it is. Even one that gets up to -60 but lasts for longer isn't going to get us to threshold. You have to have one that actually is strong enough to depolarize past threshold, or at least to threshold. Okay. Now, we're looking here somewhere where we wouldn't see an action potential occur, so we go past threshold and then it drops back down. The depolarization that we see caused here will diffuse or spread across the membrane if it reaches the axon hillock and it's depolarizing the threshold, then we'll start the action potential. But this is just showing you at other places on the membrane where we get depolarization and then we go back to rest based on the stimulus. So a weak stimulus, a medium-sized stimulus, that same medium-sized stimulus that lasts longer, and then a strong stimulus. Okay, so we get different types of depolarization depending on the type of stimulus. Okay. Now, obviously, I'm standing in front of half of the picture here because I'm trying to block the other part. We've been talking about depolarization, and so I wanted to start with that. But also, gradient potentials can go the other direction. Okay, we can hyperpolarize the membrane. Again, since they're gradient potentials, we can have weak, medium, or strong stimuli generating the change. But while the depolarizations, we're talking about getting to threshold, what are hyperpolarizations going to do? If depolarizations get us closer to threshold, what do hyperpolarizations get us?
Farther away.
Yeah, moves us away from threshold, which means that this is a way to make it harder for the target cell to reach threshold and make an active potential. When we talk about gradient potentials, in general, we use depolarizing and hyperpolarizing to describe these. When we're talking about the gradient potentials that happen at synapses, those are postsynaptic potentials, and when postsynaptic potentials depolarize the membrane, we call those excitatory postsynaptic potentials because they're going to more likely excite the cell and make it generate an active potential. Or for postsynaptic potentials that hyperpolarize the target, we call those inhibitory postsynaptic potentials because they inhibit the target from making an active potential. Now, I think excitatory postsynaptic potentials, or the idea of reaching threshold, is probably an obvious point. It's sort of the basis of what we've been talking about all along. But inhibitory or hyperpolarizing potentials might not make as much sense to you, but I can explain it very simply. Once I tell you what I'm about to tell you, you're going to suddenly be aware of something that you're not aware of now. Okay? And you're not aware of it now because there are neurons in your nervous system that are inhibiting other neurons that should be telling you information. So you might not be aware of this right now, but you're wearing clothes. Okay? So now you can feel the sleeves on your arm, you can feel the pants on your legs, whatever it might be. A second ago, you weren't even thinking about your clothes, but now you are and you're very aware of it. And that's because before I said anything, there were cells in your nervous system that were basically telling the parts of your brain that process your conscious perception of touch to ignore your clothes because they've been there all along. You know about your clothes. But now that I've mentioned them, other parts of your brain are saying, hey, he's talking about clothes. We're wearing clothes. Let's feel all of our clothes. The clothes are there. It's touching our skin. Remember, it's our clothes it's touching our skin. So the inhibitory effect that was there, getting you to kind of ignore your clothes, was removed. Okay? And if you try to think about it later on, suddenly you go, oh, yeah, I have the clothes on, and that inhibition will be removed. But when you're not thinking about it, because it's not important information for you to know, although it is very important that you are clothed at all times when you're in public. You don't need to be reminded that the clothes are there. Okay? So that's why inhibitory postsynaptic potentials or hyperpolarizing currents like this are useful. They turn off information that isn't relevant. Okay? Because if you were aware of everything at the same time, all the time, you just be inundated by information that would drive you crazy. So you have sort of off switches in your brain and they depend on those inhibitory postsynaptic potentials. Now, this picture, when I conceived it in my head, did not look anything like this, but I think it does a good job of what I wanted to demonstrate, which is how these postsynaptic potentials can add together to tell us, add together to get us to threshold. So here we have, I'm pretty sure, yellow line they're in a green color for the curve rates. Am I seeing that correctly? Okay. I had a little trouble between those two colors, but, oh, great. So we're just paying attention to the green lines and the purple lines, which correspond to the synapses represented up here. So the synapses that are colored green are the ones that are releasing neurotransmitters that cause depolarization, that are excitatory, causing EPSPs, excitatory postsynaptic potentials. And then the two that are in purple up here are the ones that are releasing neurotransmitters that cause hyperpolarization or inhibitory postsynaptic potentials, IPSPs. And when I realized this, it kind of really threw me. Right here, we go back to the yellow color, and until I figured out it was a different color, it really drove me crazy. But what they're showing here is that there's no activity at this point. So this is what the membrane's doing on its own. I'll explain it to you. So let's pretend that this is this synapse, and 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 this is this synapse. Okay, we just say all of the different synapses are represented. Each one generates a slightly different size gradient potential, postsynaptic potential, because each one's releasing a slightly different amount of whatever chemical it's releasing. And we're going to talk about what those chemicals are later on. But we can see that we can add things together or subtract out from inhibition. This little yellow part here where we see a slow decline, that's just that nothing's happening to the membrane at this point, so it's trying to get back to rest. Okay, so it's sort of falling back down, and then another one comes around and boosts it back up, and then it inhibits and boosts it back up. We finally hit threshold, and at the axon hillock, we get the action potential. Okay. So I was not expecting it to show such a long time frame, but it actually works out pretty well so that you can see each one individually. But that gets us to threshold, and we get the action potential. Okay. So the next portion of the presentation is about the synapse. So we'll talk about that next time. That'll finish off this chapter, and we'll start talking about the anatomy and the nervous system stuff. Probably next week. Probably next lecture, maybe next week. But otherwise, thanks for holding on for a couple of minutes, and have a good day. Oh, that's not a good sign.